Hey guys, Carlson here to go through video lecture number 2 of chapter 18, where we're going to talk about how urine is transported. And this doesn't occur until filtration, modification, and urine production ends in the renal pelvis. So the structures that do transport, store, and eliminate urine makeup are tract, and that is the ureters, the urinary bladder, and the urethra. Now, the ureters are these muscular tubes, and they take urine from the kidneys to the bladder here, and they're about 30 centimeters long, and you can see that they actually begin at the urinal pelvis but end at the posterior wall of the bladder, where they attach to these openings, again on the posterior side, and they're more like slits rather than holes. Every 30 seconds, they make peristaltic contractions, begin at the pelvis, and sweep across the ureters to force urine towards the bladder. Now, solids composed of calcium deposits, magnesium salts, or uric acid crystals can form here, resulting in nephrolithiasis, which we more commonly know as kidney stones. So the actual structures themselves are calculi, or kidney stones, that cause the nephrolithiasis, which is a painful thing to go through, but can be fixed fairly easily most of the time. Now, the bladder itself is a hollow muscular organ. It stores urine prior to micturition. A full bladder can contain up to a liter of urine, but however, we don't really want to get it that full. Lies in the pelvic cavity, and the area surrounding the urethral entrance right here is called the neck. It contains a sphincter that allows for involuntary control of urine discharge into the urethra. Stratified squamous line the bladder for distension purposes, so easy stretching there. And the middle layers of smooth muscle for the powerful detrusor muscle to be located, and that helps with contraction to expel urine contents into that urethra. Now, the urethra itself, again, is this area here. It extends from the neck of the bladder to the exterior of the body. It passes through the muscular floor of the pelvic cavity to form a circular band of skeletal muscle called the external urethral sphincter, okay, which is how we voluntarily control our urine output. Now, the micturition reflex, or the urination reflex, controls the peristaltic contractions of the ureters to move the urine into the urinary bladder. As the bladder fills, stretch receptors in the wall of the bladder are stimulated. Afferent sensory fibers in the pelvic nerves carry the impulse to the sacral part of the spinal cord. Stimulation of inner neurons will then relay sensations to the thalamus, and then projection fibers will carry that to the cerebral cortex. Basically, what this ends up in is a conscious awareness of fluid pressure in the bladder or the need to urinate. So this urge usually happens at about 200 milliliters full. If the volume exceeds 500 milliliters, the micturition reflex may force open the internal sphincter. Now, each increase in volume of the bladder leads to an increase in stimulation. So the more it gets filled, the more it's stimulated, the more you feel like you need to go, which is why you get to a certain point where you don't want to wait anymore. Now, 18.6 talks about balance, basically, in the urinary tract. So we're going to talk about each one. But the maintenance of normal volume and composition in the extra and internal intracellular fluid is vital to life. And there are 3 types of homeostasis that are involved. Fluid balance, electrolyte balance, and acid-base balance. Fluid balance is when the amount of water you gain is equal to the amount you lose. This requires regulation of the content and distribution of the water in the extracellular fluid and intracellular fluid, as you see abbreviated there, and we'll talk more about those here shortly. Cells and tissues cannot transport water, so we rely on osmosis, remember? So we have concentration gradients that will eliminate ion imbalances as needed. Now, electrolyte balance. First of all, electrolytes are ions released through the dissociation of inorganic compounds. And they're named this way because they conduct an electrical current to provide different functions for our body. But this involves balancing the rates of the absorption across the digestive tract with rates of loss at the kidneys. So they're balanced when there is no net gain or loss of any ion. Usually sodium and potassium is what we're talking about, and we'll talk a little bit more about this later too. Now, acid-base balance is when the production of hydrogen ions is equal to the loss. When the balance exists, the pH of body fluids remains within normal limits, which is 7.35 to 7.45. Preventing reduction of pH is difficult due to our normal metabolic reactions generating such a variety of acids, and the kidneys and lungs play key roles in maintaining this acid-base balance. Now, like I said, we're going to talk about the ECF and the ICF, which are just our fluid compartments. And the intracellular fluid contains about 60% of the total body of water, while the ECF contains the rest, so about 40%. Exchange occurs between the two, but they retain their own distinctive characteristics. So water balance is maintained normally by you eating, drinking, and then metabolic generation. 18.7, we're going to talk about blood pressure and osmosis and maintaining that fluid and electrolyte balance. So we're going to talk a little. Okay, so water movement between the ECF and ICF is called a fluid shift. And if you're not catching on to the ECF and ICF, ECF is extracellular fluid or fluid outside of a cell. ICF is intracellular fluid or fluid inside of the cell. And so this is kind of an osmosis review. The ECF becomes hypertonic relative to ICF, then water is going to move from ICF to ECF. If ECF becomes hypotonic relative to the ICF, then water will move from the ECF into the cells, so therefore the ICF will increase in volume. So again, we're going to talk more about this in class, but it's just a